Alright, this is our DP3 presentation. We are the Goldberg boys. I'm Braden.
I'm Ben.
And I'm Sam.
This is our product overview. We created a Battlefrog Rube Goldberg device. It teaches physics concepts to high school students. Our target market is 11th and 12th grade high school students and high school physics teachers. So our product contains 3 phases. Each phase aims to focus on a certain important physics concept. Our first phase focuses on Hooke's law and conservation of energy. Our second phase focuses on projectile motion. Our third phase focuses on Newton's second law. And the purpose of this product was to create a more interactive way for students to learn physics. So rather than just learning from basic lectures and textbooks, we wanted students to get more interactive and maybe have more fun while learning.
So a big part of starting this project up was our project management. So we essentially had a bunch of different tasks we wanted to hit on throughout the design process. So we created a Gantt chart, as you can see here. This was updated throughout the design process. We started off by identifying customer needs because first, before starting anything, we need to make sure we were hitting the things that customers wanted out of the product. So that's what we did first here. As you can see, that leads into establishing some target specifications and doing some IP literature research. Those tasks were done in parallel. After completing those tasks, we did some concept generation and testing and product architecture. While all this was going on, we kind of had a running economic analysis kind of just based on how our product changed throughout the design process. After that, we designed it for our manufacturer. In this case, we were our own manufacturers, but essentially it's kind of like just giving ourselves like a 3D blueprint of what we wanted to make. And then from there, we created a prototype that we played around with until we got what we wanted, and then we presented our results last week on December the 6th.
Okay, our first step in this whole project was planning the design effort, and each member of the team came up with their own concept of what they thought the product should be. The first concept was geared toward elementary school students, and its 3 main stations would focus on things such as the water cycle, multiplication, and other things they might have learned in science or math class. The second concept was also towards elementary school students, but more specifically towards 3rd graders. And these concepts were mainly math, astronomy, and spelling. And then lastly, our third concept was geared towards high school students, more specifically 10th or 11th grade students and 12th students in physics. And in these concepts, we wanted to focus on things such as conservation of energy, Newton's second law, things of that nature. And we ended up choosing concept 3 because we believe that both concept 1 and 2 elementary school students wouldn't fully appreciate in BRG, and we believe that concepts such as the water cycle or spelling would be hard to show on a BRG. As far as the customer needs go, we interviewed both physics students and physics high school teachers, and we pretty much compared the BRG to a textbook. And the main thing from these interviews we have found were that the textbooks seemed to be too expensive, they were worn easily. Sometimes students had an issue learning with these, whereas reading, they didn't get the full effect of learning where they would with a visual. So from that, we got interpreted needs such as the product needs to be affordable, the product needs to reinforce concepts, must be durable, and also must be easily accessible. And as a team, we decided that both affordability and being able to reinforce the concepts were the primary needs, whereas durability and accessibility were more of secondary needs.
For our product specifications, we needed to make sure that our product fit on a 24-inch by 24-inch pegboard. We also focused on price. We wanted to make sure that our product costed less than $80. And we have 3 stations that incorporate physics concepts, as we stated earlier. Throughout this, we needed to make sure that we utilized an Arduino at some point in our product. And another major thing was we needed to receive and eject the ping pong ball at 3.4 meters per second.
So throughout the concept generation phase, we decided, obviously earlier on as we mentioned, that we were going to go with the concept that focused on the 3 stations that have physics concepts. So anyway, we created our first concept generation here. This was our original idea that includes a spring-loaded peg here that has 3 pre-programmed buttons essentially. Each one being a different answer, one of them being the correct answer, the other 2 being incorrect answers. Essentially, the user needs to calculate how far back the peg needs to be preloaded by the spring in order to make it up the ramp. If they choose the right button, the ball will go up. If not, the ball won't go up. So essentially it rolls up the ramp here down to our second station, where the user can manually move this elevator up and the ball will get stuck behind the ramp there. Not pictured, but on top of here is an Arduino that essentially raises and lowers the gate. In order to make the ball go, they have to raise the ramp by inputting the correct Arduino code. After the Arduino code is inputted, the ball will roll down the ramp to the third station here, where you can see this hammer-based lever essentially swings on a pivot, has a little weight at the bottom so it swings better, and if the hammer is raised to the correct angle, the ball will exit the BRG. Concept 2 is much like Concept 1, although we felt that on Concept 1 we were limiting ourselves at Station 1 because with only having 3 buttons, the user didn't really have a lot of flexibility and they could just guess and make the ball go. With this one, you have more of a user interactive interface because the spring here can be preloaded to different distances from where the ball is, and essentially the user can calculate exactly where it needs to be. The measurements will be marked out here and they can kind of play around with it to see what different distances will make the ball go different heights. Like either it could go not far enough up the ramp, it could go just right, or it could fly off, so they can kind of play around with it more. It's more user interactive. For our third concept, we decided to play around with a fishing line with a weight at the bottom. It's essentially the same thing as was in concepts 1 and 2, but with this you really don't have as much of a result that's going to perform the same every time. We found that it just wasn't going to work out as well for us. For our FMEA on product 2, which is the one we decided to go with, we kind of found that there were going to be 3 different failures, one at each station. At station 1, essentially the failure would be that the ball does not go far enough up the ramp. It'll just have to cause the user to reset the ball, and the reason why it didn't go up was either because the spring wasn't pulled far back enough, or if it was pulled too far, the ball would just launch off the ramp. The recommended action for that would just be to do some trial and error and mess with the calculations to try to get the right distance of the spring. For our second station, the failure would be that the ball does not roll out the gate because the gate does not open. This would be because the user has either put in the wrong Arduino code or their calculation wasn't correct, causing the Arduino code to not operate as intended. And for the third station, the ball would not exit the BRG, it would come short because the user does not have the angle correct on the hammer. Here we have our 3D CAD model of the final design. We chose, as you can see, the ball comes in and it stays here. Pulling back the handle launches the ball up the ramp and then comes down this ramp. The user raises the elevator where the ball is then stuck behind the Arduino operated gate. Once the correct code is given to the Arduino, the gate lifts and the ball rolls to the third station where the swinging arm knocks the ball out of the BRG. Here we have an orthographic view of our first station and the isometric view as well, top, right, and front views with the dimensions as well, so it makes it easier for users to associate numbers with their calculations. And we also have the same exact sketches for stations 2 and 3. Station 2 here and station 3 here.
So as far as our product architecture went, what we did was we took our product and pretty much split both the physical and conceptual sections of the product into smaller chunks, as you see here. And what we did, we kind of grouped them up and thought that the best way to go about this would be 3 main chunks, 1 at each station. And with this, is station 1, for example, has allowing the ball to enter, moving the ball up the ramp, keeping the ball from falling off the track, and then conservation of energy, which is more its conceptual part. We figured with the 3 chunks representing each station, if we wanted to further along make a new product, where for example we wanted to keep station 1 and 2 the same, but change station 3, we could go about changing station 3 while not having to mess with station 1 or 2 at all. Next will be industrial design and our assembly time. For industrial design, the most important thing to us was our quality of user interface. We figured that if our product, its interactivity is very well, it will help the physics students more understand and it will better reinforce the physics concepts that need to be taught. Safety and ease of maintenance were of least important to us. Our product doesn't really have any sharp ends or pinching points or anything like that as far as safety goes. So we figured, obviously we want our product to be safe, but there's no real harm in the product itself. And for ease of maintenance, we figured our product is durable when we make it, and our goal is that it won't have to go under any maintenance after the user has obtained it. And then more on industrial design, we focus more on the ergonomics part of it rather than the aesthetics. We do want a good looking product, but that's not the most important thing to us. As we stated earlier, the quality of user interface is more important. For assembly time, we predicted that roughly each product would take about 125 seconds to make, but after using a table, we discovered that it takes about 115 seconds, which was pretty close to our predicted assembly time. Then using a rate of 25 cents per minute, we calculated that it would take roughly 48 cents to assemble one product.
So here's a simple cost breakdown of what this thing would cost us to produce ourselves. We have 5 table saws, 5 chop saws, and 5 drills. This is assuming that we have 5 employees working on these at a time. And then we've got miscellaneous equipment such as screws, springs, extra pieces of lumber, anything of that nature. And then we've got our building costs, our labor costs. Our labor costs come from a rate of $15 an hour with 5 employees working an 8-hour day. We're assuming that we're going to be able to create about 40 units per day. That comes from cutting the lumber, assembling the BRGs, etc. Looks like our lumber was going to cost us about $5 per unit, and each Arduino is going to cost us $40 per unit. So as you can see here, at 100 units, we're running about $81 per unit. That's a cost to us, which isn't really going to cut it for the $80 we want to sell it at. But as you can see, as we get down here into 500, 600, up to 1,000 units, we're running around $50 per unit, which makes $80 selling point totally feasible for us.
So some possible improvements moving forward. For station 1, we found that when the ball entered, sometimes it didn't always stay directly in the center of the wood. So our goal is to make a small pivot or divot in the wood so that when the ball enters, it sticks directly in the center of the wood. And the rod attached to the spring will consistently hit the ball right in the center of gravity. For station 2, we decided that we would use a different Arduino code. So as of now, the user just has to enter a number between 1 and 100 for the gate to open. We decided that a better way would be for the user to have to calculate how far the ball would land from the elevated ramp. And if they input the correct answer within 10%, then the gate will open. And for station 3, very similar to station 1, we also decided that a divot in the wood would be perfect so that the ball stays directly in the center of the wood, and the hammer on the pendulum consistently hits the ball right in the center of gravity, causing it to leave at the proper exit velocity. And here's our final product. So we have our station 1 here with our rod attached to the spring, and it goes up, goes down here, and then we enter station 2. User lifts here, and then the ball comes to a stop at the Arduino gate, rolls down into our station 3 where we have our pendulum hammer, hits the ball out and exits, and that is it. Thank you.